Welcome to a GRE Basic Math Refresher. This is Emily Sledge, and I'm going to be throwing a lot of questions at you today that will require some scrap paper work on your part. And as I do, every time I put up a question, I will pause for 2 or 3 seconds before discussing the answer. In those 2 or 3 seconds, I'd recommend that you find the pause button on your video player and pause it, work the question yourself, and then come back for the explanation. In doing so, I hope to make this as user-friendly as possible. People can take the time they need for each question. And if you're pressed for time, you can just skip the pausing and solving and just stay with us and see the explanations at least. So let's begin. We'll begin with a few math terms, kind of a glossary at the beginning. So integers, these are the counting numbers that we all know and love. You count up, you count down. So negative numbers can be thought of as the countdown numbers, t-9, t-8, t-7. And so in this question, which are integers? Turns out all of them are, except 1/2. 1/2 is not an integer. It is a fraction. Now, although it looks like a fraction, 4/2 is actually the integer 2. It reduces to an integer. So even though it looks like a fraction, it's written in fraction form, this value 2 is still an integer. And the point there is that integers can be written in fraction form, and occasionally you'll do that as part of other calculations. So for example, 9 over 1 is still the integer 9, even though written as a fraction. Odds and evens. Evens are divisible by 2. Odds are not. Odds are integers that are not divisible by 2. We've covered positives and negatives. It's helpful to think about a number line. When I was in first grade, I remember having a number line stuck on my desk, and I still go back to that way of thinking on certain standardized test questions. It's a very helpful concept to think about left versus right of 0 on that number line. Sum, difference, product, and quotient. These are the math symbols that we all learn probably first in our math careers. And we'll be doing some operations today with those. And remainder is what's left over after division. So, for example, 9 divided by 4, the 4 goes in 2 times because 8 is less than 9, but 8 leaves 1 left over. So 9 divided by 4 is 2 with a remainder of 1. 0 is worth its own special mention. It's not positive, it's not negative, it is the one exception. It is an even number. That's a frequent question for people. And think about why. 0 divided by 2 is an integer, and that's the test that you use for even numbers. Another way to think about that is that all integers alternate, even odd, as you go through the number line. And there is 0 right between 2 odds, -1 and 1. You can divide 0 by anything. We just talked about how it's divisible by 2. It's divisible by any other number, except for 0. You can't divide anything by 0. And that's what we mean by epic fail here. So in the 2 bottom examples, without knowing what x is, you can't really do anything and solve either of these. But I will say that if you saw something like this on the GRE, most of the time they'll go ahead and tell you, hey, x is not 0. In other words, we're not doing something illegal here. On this example on the right, it would probably tell you x is not equal to 1. Okay, just so you wouldn't have to worry about that being an illegal move. Distinct and inclusive. These are terms that are important for figuring out what numbers you need to think about. So distinct numbers are different. Okay, so if x and y are distinct, that means they're not equal to one another. Inclusive means include the numbers at the ends. So if they give you a range from 3 to 5 of integers, that's not just the 4 that's in the middle. Include the endpoints of 3 and 5. And people often ask about, well, will you ever see exclusive? I haven't seen that on the GRE ever. So my guess is if they restrict you in any way, it'll be with the word inclusive. Absolute value bars. They take a number and they make it positive. So another way of saying that is if you take -9, for example, and turn it positive with absolute value bars, it becomes 9. But originally, -9 was 9 away from 0 on the number line. So that's a useful way of thinking about absolute value. You can have a positive distance if you go left on the number line. You can have a positive distance if you go right, and that's what absolute value is. So if we do this actual calculation, the thing to remember is that absolute value bars work like parentheses. You have to tackle everything on the inside before you do that whole turn it positive operation. So if we do everything in the bars, we get -10, and then we turn it positive. And so the result overall is +10. Digit questions most often ask about the units digit because there's some cool shortcuts with units digits. Chief among them is when you take the product of two integers, when you multiply them together. And in fact, this may be something to do on your own paper. Multiply these huge numbers out with one another, longhand, right? Don't use your calculator. Do it on paper. And what you'll quickly see is that the only calculation or the only step in the calculation that affects the units digit of the outcome is when you do 3 times 7. And since 7 times 3 is 21, you would write down a 1 on your paper and carry the 2 when you're doing old school multiplication. As such, you can shortcut this. If they ask you about the units digit of the big long number, just skip the rest of the calculation, look at the units digit product. And so the answer here is 1. Prime numbers, just to refresh your memory, here are the first 10 primes. These are worth memorizing or at least being prepared to recognize them as prime when you see them. So if you run across 23, think to yourself, oh yeah, one special property is that it's prime. And just a quick note, notice that 1 is not on this list. And that's based on the technicality that 1 is only divisible by 1, which is itself, okay? And primes have to be divisible by exactly 2 numbers, 1 and the prime. So that implies that the prime cannot be 1. All right, also, notice that 2 is the only even prime, the only one. Higher even numbers are all divisible by 2, so they have a factor other than themselves and 1. I'll pause here while you read through some of these examples and notice that some of the phrasings are different, but they lead to similar operations. So for example, when you take a percent, you're multiplying. And you do the same thing, of course, when asked about a product, because product means multiply. You divide in several cases when asked for a quotient, when also asked for a ratio, or even an average. So that brings us to fractions. Fractions are about implied division. And just to save saying numerator and denominator a bunch of times, I may just call that top and bottom. And we're going to talk about the various things that you can do with fractions, namely alter their appearance, add and subtract them, multiply, and divide. So alteration is changing the appearance of a fraction without changing the value. And you do this by operating the same on both the top and the bottom, multiplying or dividing by the same number. So 8 over 20 reduces to 2 over 5, and that's done by dividing both the top and the bottom number by 4. We've done the opposite move on that second one, right? We multiplied the top and the bottom both by 4. So why would you want to do this? On the GRE, if it's a multiple choice question, the answer will always be in most reduced form. So you may do a calculation and reach the conclusion that the answer is 8 over 20, but that's not going to be listed among the answer choices. It's going to be up to you to reduce that and, figure out that that corresponds to a 2/5 answer. So you can then pick that. Why would you make a 1/5 into 4/20th? After all, that's less simple. But sometimes you want to do that if you, for example, need to do an addition of 4/20ths with something else that also has 20 on the denominator. And the reason you can get away with this is that by doing the same thing to top and bottom, you're essentially multiplying by 1, which doesn't change the value. All right, I've already alluded to this. The need to have a common denominator is for addition and subtraction moves. So notice that we've changed in the second example 2/5 into 6/15 by multiplying by 3/3. Both top and bottom number became bigger by a factor of 3. And that was with an eye on making this common denominator of 15. And it's only after you create that you can subtract. Once you're at this point, it's just a simple matter of taking 6 minus 10 and getting the new resulting numerator. Multiplication, you do not have to create a common denominator. You just go ahead and multiply across the top, you multiply across the bottom. Straight across, and you've got your new top and bottom. One tip is to reduce as much as possible during intermediate steps. So you might notice in that second example that 25 and 50 have a shared factor of 25, 4 and 12 have a shared factor of 4. So rather than multiplying 25 times 4 and getting 100, and 12 times 50 and getting 600, and then reducing at the end, reduce as you go. And just keep track of what you're doing. Think about what's left over, if there is anything left over. When you divide by 25, 1 is left over on the top and 2 is left over on the bottom. All right, here's another one. I'll pause here if you want to pause the recording and try it yourself. All right, lots of shared factors on top and bottom. So some canceling can happen. And you may notice that I haven't canceled all the way here. I did that to make the point that even canceling part way would be helpful. So on top we have 4 times 3, 12. On the bottom we have 2 times 6, 12. Very easy to see that reduces to 1. Okay, so even partial cancellation is better than none. With division, this is kind of the fancy move. If you divide one fraction by another, or if you divide something by a fraction, the top could be an integer, but if the bottom is a fraction itself, you flip that bottom fraction and then multiply the top by that. Okay, so 5/6 stays the same, and it's that 5/3 that flips and becomes 3/5. And there you follow just the regular multiplication rules. The 5 canceled here. 3/6 is 1/2. All right, here's a challenge. Pause. And the thing about this challenge is that you can't just dive right into flipping the bottom fractions. Those red parentheses are there as my recommendation to you. Parentheses are free. Use them. They are your friends. Okay, so the parentheses to me remind me that I need to add those 2 bottom fractions before I can divide by the bottom there. You have to get that as one single fraction. Combine those 2. And when you do, you have to go to a common denominator of 6. You get 5/6, and at that point, you can flip it. So very common mistake for people to flip them as they are given. 2/1 plus 3/1, and they end up with 5, and that's a mistake. Okay, so don't do that. Add first. 2 more questions. I'll do a pause. As you pause the recording, solve these yourselves and then come on back. All right, so this first one is very similar to that challenge we just did. in the sense that there's that 2 minus 2/3 in the denominator. You can't divide by that denominator until you first deal with that. So I've put those handy dandy parentheses in there. Always remember that you need to do subtraction first there. Okay, so that gives you 4/3. Now you can flip the denominator and you get 1/8 after reducing. Now the second example, I wouldn't necessarily do it this way. What they've shown here is, writing 9 and 15 in their fractional forms. They've just put a 1 in the denominator. So the idea there is, it's the same old fraction times fraction multiplication that we've been doing. Just multiply across and reduce. I think many people, though, would look at this from the outset and say, hey, I know what 2/3 of 9 is, right? I can think that through in my head. I know that's a 6. If you went straight from that to this line of the calculation, great. More power to you. 18 is the answer. Okay, so we've been talking about moves that you can make with fractions, but why do we do this? Why are there so many questions about this? And that is because fractions show up in real life. They're used to indicate portions of things. So you can imagine the wide variety of word problems that are involved. You can think about books in a library. Some portion of the books at the library are hardback books. Some portion of the books are paperbacks. Lots of real life applications for this. And here's one of them. All right, hopefully you've had time to think about this one as you pause the recording. And in reading the language here, notice that there are several ways of talking both about whole and about part. 4/5 is obviously talking about a part of something, right? It's a fraction. But the $1,400 is also a way, and monthly taxes also a way of talking about a part of Sally's money. Okay, she has taxes and she has after-tax money. So if we go and label this, gross pay is Sally's whole amount, but she keeps some part of her money and she pays taxes with part of her money. Okay, so there's two mentions of the taxes part. Okay, one is the directly given to us, the $1,400, and one is sort of implied. Okay, so after taxes, Sally keeps 4/5. So that means she paid 1/5 of her gross pay as taxes. Okay, so we have two ways of expressing her taxes. They have to be equal to one another, so set them equal. 1,400 equals 1/5 of the gross pay. And if you do the calculation, her gross pay is $7,000. So watch out. If you got a different result, it's possible that you said that her taxes were 4/5 of her gross pay, which would not only lead to the wrong answer, it would be very burdensome for Sally to pay that much in taxes. All right, there's another kind of question that crops up a lot that involves fractions, and that's everybody's favorite, probability. Probability is basically just, what's the chance of of a certain outcome happening divided by the number of chances, other possibilities, right? Total number of possibilities. So with that in mind, think about winning possibilities versus total possibilities on this one. All right, so total possibilities are, there's 12 marbles in the bowl. And they do clarify that all the marbles have an equal chance of being picked. You could pick a red marble, a blue marble, or a white marble. They're all included in those 12. And most of the action here is in figuring out how many white marbles there are. If there's 12 total, 5 are red, 4 are blue, well, it's the remaining ones that are white. So we're already halfway there. Think about the top of that fraction and the bottom. So 3 is the number of white marbles, 12 is the total number of marbles, and that reduces to 1/4. Fractions, of course, imply division. So we'll change gears a little bit here while still keeping that in mind. A lot of questions ask about divisibility on the GRE, and they do that with differing language. Here's an example of several different ways of saying much the same thing. So be on the lookout for that language. And in fact, that variation in language can lead to some confusion. So it's worth reviewing this real quickly here. Looking at 12 in all cases, notice that multiples are different from factors. So multiples of 12 are big numbers. You arrive at this list by multiplying 12 times various integers, right? So you get larger and larger numbers as you go up. Factors of 12, though, are limited to numbers that are smaller than 12. They have to go into 12, smaller than or equal to 12. 12 cannot have a factor that's larger than 12. For example, 12 divided by 24, not an integer. Okay, so 24 is not a factor of 12, even though it's a multiple. From factors, it's a shorter list if you look at prime factors, because some of the factors of 12 are not quite prime. 6, 4, 12, not prime, but they're factors. The prime factors of 12 are the prime numbers that multiply to give you 12. So if you break down 12 as far as it'll go, 4 times 3 is not as far as it'll go. You can break the 4 into 2 times 2. Notice 1 is not a prime, so it's not part of the prime factors. And the prime factors get asked about the most on the GRE. I think that's because the prime factors of any number are kind of like that number's fingerprint. No other number has those same prime factors. And the prime factors of 12 are always 2, 2, and 3. And of course, back to that distinct language, distinct just means different. So the distinct prime factors are 2 and 3. The 2 is repeated. So if we eliminate that repetition, we're left with 2 and 3 as distinct prime factors. Okay, so how do you get prime factors? How do you take the fingerprint of a number? The factor tree is a really convenient way to do this. This is, I find, the favorite of most people because you keep track of each of your steps. Smaller numbers can kind of be broken down in your head, but bigger numbers, you kind of want to break it down in pieces, right? 5 times 21 gives you 1 prime, but you still have to break the 21 further. So the prime factors of 105 are 5, 3, and 7. Factor tree, very convenient when you're dealing with a very large number. You might want to do this one yourself. I'll pause here. And if you do, it's clear that 147,000 is divisible by 2, right? It's an even number. But if you start your tree with 2 times whatever half of 147,000 is, your tree's going to get very long if you keep peeling out the smallest prime like that. So for large numbers, I'd recommend doing your first split in the tree with the 2 largest numbers that you know for sure go into 147,000. Clearly 1,000 does, so that's a good place to start. Another recommendation, this is the way my math teacher taught it to me. I don't know if other people heard this in the past either, but the recommendation was to circle the fruit at the end of the factor tree branches. In other words, circle the primes when you get to them. It just makes it a little easier at the end to kind of tabulate those up, count how many 2s, 3s, 5s, and 7s you have in this case. And that's handy because then you can summarize it in exponent form. This tells us that we have 3 2s, 1 3, 3 5s, and 2 7s. Okay, so we can use prime factors to simplify our checking of numbers. And one of the rules that you can use is listed here. I paused to give you time to read this rule. And I'll tell you, I kind of don't like this rule because I find it very difficult to remember it, honestly. I know this is one of those that would go right out the window on test day for me. So let's look at what the rule actually means. If we say that y goes into x, it means that like x divided by y is an integer. When you make y go into x, it goes in an even number of times, like an integer number of times. So looking at two number examples, 2/3 is a fraction. In other words, 3 does not go into 2. And we kind of know that from experience. 6 divided by 3, though, gives you an integer. In other words, 3 goes into 6. Now, why does 2/3 end up being a fraction and 6/3 end up being an integer? You can probably see it. It's because of what the numerator has going for it. 2 doesn't have a 3 to cancel that 3 out of the bottom, right? So you're stuck with a fraction. Whereas 6 has a 3 as a factor. 6 can be written as 3 times 2. So the 3's can cancel. And the denominator goes away, leaving an integer. So that's what this rule basically means. The x in the numerator must be able to cancel all of the y. In other words, leave nothing in the denominator. So if you're ever stumped and you know that this rule exists about what prime factors are necessary, write it as a division problem. I think that's so important. When checking divisibility, remember it's about division. Okay, so with that in mind, take a look at this one. On the GRE, since you have a calculator, you could just do 147,000 divided by 8. 147,000 divided by 35, divided by 35 again to test those first two choices. Totally fine to do that. But you can also use the prime factorization to realize that you get an integer result. So 8 is 2 times 2 times 2. That's going to go into 147,000 if 147,000 has at least 3 2's in it. And sure enough, it does. In other words, this number's big enough, has all the right components to cancel 3 2's out of the denominator. And the same check applies here. 35 squared is 5 times 7 times 5 times 7. Do we have 2 5's and 2 7's? Yep. Same check. Do we have at least 2 2's and 3 5's? Yep. So all 3 of those choices are correct. Here's another one. Take a moment here. And this question, I think, is a good place to make the point that you can get carried away with thinking about prime factors. You don't always have to think about prime factors. Divisibility questions are about division. You can often fall back just on doing the division. And in fact, that's where I would start here. If 50x must be divisible by various numbers, test out those various numbers. 50x over those numbers. Okay, so that's straightforward enough. See what cancels and see what's left over, right? So 25 is an integer. 2 times x left over from the second one is an integer. How do we know? Because x is a prime number, it must be an integer. And it's with the third one we see a failure. 50x over 15x reduces somewhat. The x's cancel, 5's cancel, but we're still left with a fraction. So that's the one answer that is not correct. And looking back, we can see in terms of prime factors why. 15 in the denominator has a factor of 3 that 50 simply doesn't have. So there's that rule at work. 50x would have to have a factor of 3 for that to be divisible. Or 50 itself would have to have a factor of 3. All right, exponents. Switching gears a little bit here, but if you're rusty on exponent rules, the thing to remind yourself is that exponents are just a fancy way of writing multiplication. So if you're ever stumped on an exponent problem, just write it as a multiplication problem. All right, so 5 to the 4th, write it out as 5 times 5 times 5 times 5. And you can sometimes need to translate words into a multiplication problem that can be written as an exponent problem. So for example, if you talk about some number increasing by 10%, well, that's like multiplying that number by 1.1. And if you do it 3 times, well, that's looking like kind of an exponent type operation. Same thing multiplied multiple times, 3 times in this case, that's your exponent. All right, so a few rules about exponents. And first is when you multiply things that have the same base, you can add their exponents. And think about why. A to the 5th is 5 a's multiplied together. And you're multiplying that with 3 a's multiplied together. So overall, that's a string of 8 a's multiplied together. Okay, so all this is a shortcut for writing it out and then counting them out. Okay, so the point I want to make here is that it won't matter whether those exponents are positive or negative, or even whether they're fractional. Does not matter. This rule still applies. So 3 plus minus 2, exponent of 1. 1 plus 2 plus 1/2, 3.5. When you divide, the same kind of principle is at work. We've got 5 a's multiplied together on the top here, 3 a's multiplied together on the bottom. 3 of the a's on the top can cancel out 3 of the a's on the bottom, and that'll leave 2 a's on top. So the shortcut is just subtract, okay, instead of writing it out and doing the actual cancellation. So division means subtract exponents. So 5 minus 2, 3. Don't get weirded out if there's negatives, but do be careful with them. 4 minus minus 1 means 4 plus 1. The exponent here is 5. When you raise an exponent to an exponent, sometimes people say power to a power, it's multiplication again. So fancy multiplication here, fancy multiplication here. So we've got 2 a's 4 times. If you actually wrote that out, you'd have 8 a's written down. All right, so multiplication again does not matter if either of the exponents is negative or fractional. Just go ahead and do the multiplication. 3 times minus 2, minus 6. 2 times 1/2, well, that's just 1. Here are some common exponential sequences: the powers of 2, the powers of 3, 4, 5, and 10. You should take some time now, if you have the time, or later, to extend these lists. Write them out a few more terms, and also write out the sequences that aren't on this screen: the powers of 6, the powers of 7, 8, and 9. And see what you can see. Have a passing acquaintance with the numbers on these lists. That doesn't mean you need to memorize every last sequence, but do be prepared to recognize the numbers when they crop up on the test. So for example, the next number on the list of powers of 3 would be 729. If I see that on the test, it's a very large number, but I also recognize that it's a large special number. It has the property of being one of the powers. And that's enough to prompt me to look into it, that recognition. So do I know instantaneously it's 3 to the 6th? No, but I'm prompted to check that and figure it out. By the way, 729 is also on the list of powers of 9. It's the 3rd power of 9. So that's one way these numbers are useful. Another way they're useful is that they follow some patterns. So take a look at the list of tens. Notice how all the units digits there are 0. Likewise, the list of 5. The units digit is always 5 in any power of 5. The 4s are fun. They alternate from 4, 6, 4, 6, and that goes on forever. The longest pattern for any of these sequences is 4 terms long. And so we see that in the 2's and the 3's. So notice the 3 has 3971, then 3 again. It would be 971 if you carried that out. This problem shows how you might use some of that knowledge. Pause the recording, take a moment to work this out yourself, and then come on back. So 25 is obviously 5 squared. The lower powers are the easy ones to remember. And that's what you'd need to do to solve a question like this. In general, you want to create the same base to be able to do math in an equation, get things in common terms. So putting 25 in terms of 5 squared, substitute it in. We just use our exponent rules. Power to a power means multiply. And by having a common base, it lets you sort of ignore it. 5 to the x would only equal 5 to the 14 if x itself were 14. So once you get to the stage where you have a common base and a single exponent on each side of an equation, as long as the base is the same, you can just set the exponents equal. Use that again here. And this problem has the slight twist of having answers with variables in them. Take a moment, think about this one. All right, so we have a base of 10 on the left, base of 1,000 on the right, but that is a power of 10 itself. And we've got two variables in our respective exponents. So, as always, make the base the same. And a quick trick with powers of 10 is you just count the zeros. So 3 zeros means 3 is your exponent. 10 to the third is equal to 1,000. And sub it in. And powers to a power means you multiply the 3 and the y. And you're at that same point where you have same base on both sides. Just set the exponents equal. If 3x equals 3y, x and y must equal each other. And because this is a variables in the answer choice problem, we could have taken the approach of picking numbers. Or we could even just check what we did there with numbers. So if y is 2, the right side is literally 1,000 times 1,000, which is 1,000,000, which has 6 zeros, so it's 10 to the 6th. So if 10 to the 3x equals 10 to the 6th, 3x equals 6. And x is 2. When we plug in, then the correct answer will give us 2. So if we plug in 2 for y, we should get what x equals, which is 2 in that case. Or you could just say, well, okay, x and y are equal the same number, and just go directly there without plugging. Quick drill to put it all together. Use those rules that we've reviewed. Pause the recording, take a moment, come on back. All right, when the base is the same, you're already set up to do the math. So you've got to just think about what is the operation. In the top problem, you're multiplying these powers of 5, which means you add the exponents. So adding those up, you get an exponent of 5. 5 to the 5 is the answer. We're also set up with the same base in the second problem. G is present there. But in the denominator, you've got a power to a power. Combine those by multiplying. So then you have g to the 12 over g to the 12. Same on top and bottom. That means that fraction is equal to 1. Or you could explicitly use the rule about dividing. When you have exponents, you subtract the exponents in order to divide. So 12 minus 12 is 0. We end up with g to the 0, and anything to the 0 is 1. In the last one, 3 and 9 different bases, but 9 is a power of 3, so you can convert a couple different ways. You could convert and sub in for 9, sub in 3 squared as we've done there, and carry it through. Or you can change 3 squared into 9 to the 1 and get your answer in terms of a base of 9. So you'd have to look at the answer choices in that case and see what form they took. All right, maybe here's a little extra credit set. See if you can mine your memory for what these exponents do. And this set is in here to remind people about those oddball exponents. What is a negative exponent really doing? What is a fractional exponent really doing? Well, let's take a look. A negative exponent means it's you're really dividing by a to the positive 5 here. Negative exponent, if you want to change it positive, you put it on the bottom of a fraction. Another way to say that is if you change the sign of the exponent, you flip it to the bottom. And I have had students in the past who are so weirded out by the negative exponent that, their best first move is to just change all of those into their fractional form, more like this. That way, they really can see what's happening. You're dividing by a to the 5. This is a little bit more clear to them what the real math move is. So try that out if you find that you're struggling with these. When you have a half as your exponent, what that really means is take the square root. So in much the same way an exponent of 2 means you square the base, an exponent of 1/2 means you take the square root of the base. And putting those ideas together, a to the minus 1/2 means you are both taking the square root and you're really dividing by a square root of a. Okay, so you put it on the bottom because of the negative, you take the square root because of the fraction. And by the way, other fractions are possible as exponents. So if you saw an exponent of 1/3, that would be called the cube root. Those don't come up too much on the GRE though. Switching to geometry, here's some formulas for area, various shapes. So rectangles, most people recall those pretty easily. Length times width is how you get your area. For triangles, it's base times height divided by 2, or you might more readily remember it in this form, 1/2 base times height, same thing. Area of a circle is pi r squared. And the circumference of a circle is 2 pi r. We mentioned circumference here because many people mix up those two equations. If that happens to you, remember that area should be in units of like square inches. Area of a room is in square feet or square meters. So in the area formula, you do want to square the radius, which could be measured in inches, getting inches squared as a result. But for circumference, that's a measure around the outside. That's a linear measure. It should be in inches or some other linear unit of length, and so you don't want to square the r when using the circumference formula. Right triangles are special because of Pythagorean theorem, which you see down here. So the Pythagorean theorem lets you calculate one side of a triangle based on the other two. And right triangles are the only ones where the Pythagorean theorem works. So don't overuse this formula. And so you would definitely have to be told that you're dealing with a right triangle. And they do so here by that right angle measure or indicator. This tells you this is 90 degrees. So with some numbers, you can plug in. And if we plug in here, right, we're going to square 1, we're going to square 2, get 1 and 4, add those up and you get 5, so c squared is equal to 5. And I should mention that a and b are always the two sides that are perpendicular to each other, and c is always your hypotenuse, the long side. And so c here would be root 5, and that is a crazy decimal, goes on forever. GRE tends to steer clear of messy answers like that. they can definitely come up, but a lot of GRE problems are built on these triangles where you don't get messy answers. So these are the Pythagorean triples. You should memorize these. These are the known triangles that don't have decimals or fraction side lengths on any of the sides. So notice that 3, 4, 5 checks out. When you square 3 and square 4, you get 9 plus 16. That brings you to 25, and the square root of 25 is 5. So going left to right on the screen, that's pretty much in order of frequency that these crop up. So the most common is 3, 4, 5, and then its variant, which is just the 6, 8, 10. Same triangle blown up by a factor of 2. And then 5, 12, 13. There are some others out there, but they are far less frequent. Some other triples that you should memorize are those for right triangles that have special angle measures. So one is the 45, 45, 90 triangle that would also show up as half of a square. So notice that the side lengths are the same, just as they would be in a square. And memorize that the diagonal there, or the hypotenuse, is always root 2 times the side length. In a 30, 60, 90 triangle, the shortest side is across from the 30-degree angle. The longest side is the hypotenuse. It will always be twice as long as that short side. And the middle side is the one across from the 60-degree angle. That's always root 3, or about 1.7 times the shortest side. So memorize times 1 times root 3 times 2. Those are your multiples for the sides. Here's a problem for you to think about and put this all together. And the calculation's a lot faster if you can skip using Pythagorean theorem as you think about AB, and instead just recognize, hey, it's a right triangle. 2 of the sides, the hypotenuse is 10, one of the other sides is 8. That means the third side must be 6. It's a 6, 8, 10 right triangle. You can get there using Pythagorean theorem, but you save some calculation if you just recognize it. So if AB is 6, that's the diameter of the circle, so the radius must be 3, and then just plug it into the circle area formula. Area of the circle is 9 pi. When solving equations, here are some rules that you should follow. One is that if you can simplify, you should. So within those parentheses there, there's a couple things you could do. You could distribute the 5, right? 5 times 3, 5 times minus 1. But that's unnecessarily complicated. Since 3 minus 1 is something you can do something with now, go ahead and do that. And then you just end up doing 5 times 2. Much simpler. So simplify when you can. Another rule of thumb is to combine common variables. In other words, get all the variables on one side if you can, get all of the constants on the other. So they're doing that in this example. Notice first the 5a is subtracted from both sides. That eliminates it on the right and groups the a's on the left. 20 is then subtracted from both sides. That gets rid of plain numbers on the left side and groups them on the right. Third rule is that if you have fractions, try to get rid of them. So get them out of get denominators out of there, especially if those denominators have variables. Because in its current form, you cannot do anything with 4a over 3 plus a. It is illegal to split that up. So you can't say, oh, that's equivalent to 4a over 3 plus 4a over a. That is not true. You cannot do that. You can't split that into 2 fractions. What you have to do is get that variable out of the denominator. And I've put parentheses in there, as we've seen before. Parentheses are your friend. You have to move that whole denominator as a group, and the parentheses serve as a reminder of that. So when you cross multiply here, you end up doing 2 times that whole thing in parentheses. All right, try this out yourself. Solve for a variable, pause the recording, take a moment, and then come back. All right, parentheses are here, so we'll begin with that. Remember, PEM does the order of operations: parentheses, exponents, multiplication, division, addition, and subtraction. So we'll deal with the parentheses first by distributing that 4. And I've kept the parentheses there just to show where that came from. 4 times x and 4 times 3, that's inside the parentheses in the second line. But at that point you can chuck them because you're looking at just addition and subtraction at this point. We'll combine by addition, 12 and minus 8, or more appropriately, we'll subtract and carry it out from there. I like the idea of checking real quick. It doesn't have to be on paper. If you've answered a question like this very quickly, take the few seconds to plug that 2 back into the very first original equation. So if we do that here, x plus 3 in parentheses is 5, and 4 times 5 is 20, minus 8, yep, that's 12, and we know we're right. All right, so try it again. Don't worry about the t to the third right away. First get that t to the third by itself and then worry about the exponent. So to do so, we're going to make a few simple moves, addition and subtraction type moves. As long as you do the same thing to both sides of the equation, you're always good. So in the first step, we've subtracted 1 from both sides. In the second step, added 2 times t to the third to both sides. And now that t to the third is almost by itself, you just got to divide both sides by 2. And solving from there on out is really just a matter of looking at 27 and asking yourself, 27 is a third power of what? So hopefully you've memorized those exponential series and you know that's 3 to the third. Now, by the way, we can trust that result. We don't have to worry about a potential negative solution because 3 is an odd exponent. Odd exponents do not hide the sign of the base. So it would be a different story if we had reached a step in this calculation that was 9 equals t squared. Well, then t could be equal to 3, but it could also be equal to negative 3. All right, and so just something to be mindful of whether your exponents are even or odd. Next question for you has 2 variables, 2 equations. Solve for both of those variables. And one way to do so is by substitution. This question lends itself to substitution because the second equation is already solved for k. K is here by itself. So what you can do is replace k in the other equation with the h plus 18 it's equal to. So that's done here. Through this solution, just follow the arrows. You first sub in from equation 2 into equation 1, and you get a solution for the variable that remains, for the h. To get k, you'd have to plug back into either one of the original equations. Here they've plugged into the second one, and get k. And as a final double check, always a good idea if it's really fast, as it is here, double check by plugging both of your solutions into the other equation. The h plus k must equal 40, so 11 and 29 check out. Here's another one for practice. Pause and then solve. This is meant to illustrate what you do when substitution isn't you're not set up to do substitution right away, when there's an intermediate step that you have to take first. And that's with that second equation. So always survey your equations that are given and see if you have a variable by itself with no coefficient, or more accurately, a coefficient of 1. You can get y by itself easily because it's not times anything. So do that as your first move and then sub in. and go through the motions. You get your x, plug into either of those original equations, and get your y. And as a quick check, I would go back to one of the starting equations that I didn't use as much. If x is 5 and y is 2, then 7x plus 4y is 35 plus 8, and that is indeed 43. So mental check, good idea. Sarita and Bob. So word problem, you'll have to pull out some equations here and then solve from there. So this is meant to illustrate, of course, you're going to be solving some equations, but here you have to come up with those equations on your own first. You have to translate from words into math. So a couple words about that. First, give variables, use useful variables. So don't make it x and y unless you have to. S and B makes it easier to keep track of who's who. And Sarita and Bob each contribute to the cost of a $40 gift. Stop there. Don't try to process all of the words at once. Just go sentence by sentence or clause by clause. Okay, so S plus B equals 40. Write that down and then read the next part. Bob contributes 12 more than Sarita does. So here's a tip about language. When you see comparison words like more than, the noun that follows those comparison words is what you want to attach the number to. So more than Sarita means we're going to do the plus 12 on Sarita. So S plus 12 equals B. Another tip is to look for the verb in a sentence. So contributes is that verb. Generally speaking, with few exceptions, the verb tells you where the equal sign goes. So Bob equals 12 plus S is literally how that reads. And you can check it out too if you're prone to misplacing the 12 or similar errors. Quick check with a number example. So if Bob contributed $13 and he contributes 12 more than Sarita does, I'm just looking at the language here, then Sarita must have contributed $1. I don't care if it jives with the other thing about $40. I'm just looking at that second sentence. So 13 and 1 are valid answers or valid test cases. And notice that 1 plus 12 equals 13. So this checks out. If you had misplaced the 12, the numbers would not check out. And that would tell you, fix it. And from there on out, it's just substitution and solving. And as always, a quick check at the end. So notice this checks, or this calculates Bob's contribution by looking at the total of 40. And you can do a quick check with the other equation. $26 is 12 more than Sarita's 14. Must be the right answer. All right, inequalities are fun. In many respects, they're like solving an inequality is like solving an equation. Notice the first step here is they've added 15 to both sides. So as with equations, as long as you're doing the same thing to both sides, you're doing the right thing. But with inequalities, there are some additional rules which have to do with multiplying or dividing by a negative number. If we want to divide by -5, you must flip the sign. Multiply or divide by a negative, flip the sign. And this is because if you look at a number line, the negative part of the number line is like the mirror image of the positive part of the number line. Everything is backwards there. So think backwards means you flip the sign. To put that in another way, if we compare 8 and 3 positive numbers, the one that has like the bigger absolute value is on the right of the smaller one. But on the other side of the number line, comparing -8 and -3, the bigger number is on the left side. So notice the sides have kind of swapped. And that's what this sign flipping is all about. Here's an extra credit problem for you. And if you're like a lot of people, the first move that you made was to say, hey, I've got an x on both sides. Why don't I divide that out? This can simplify that way. With inequalities, you don't want to do that. For one thing, if you don't know the sign of that variable, you don't know whether you're multiplying or dividing by a negative number. And you don't know whether you need to flip the sign. And in fact, here, one way to see that this is wrong is to look at negative numbers. So plug in a negative x. When you do that in the original equation, you get a positive number. Negative squared is always positive. But 3 times a negative x is going to be negative. And a positive is always larger than a negative. That's why it doesn't matter what negative number we plug in for x, they're all going to be solutions to this inequality. So by dividing by x, we lost all of those solutions. Okay, it is true that x could be greater than 3, but we've overlooked a broad array of other valid solutions. So long story short, just don't do that. Don't divide by a variable. Absolute values. The rule with absolute value is that those bars turn whatever is inside positive. So one way to look at this is, some absolute value of something is equal to 11. How does that happen? It happens if what's inside is just 11 to begin with, then the absolute value bars don't do anything. Or you could get equals 11 if you started with negative 11 inside those bars. Absolute value of negative 11 is 11. So within every absolute value equation, there's really 2 equations, and you should write these down on your paper separately. Set the stuff inside the bars equal to 11 and set it equal to negative 11. Solve those separately and see what you get. And then check both solutions. Okay, so double check real quick in your mind. 2 times 9 is 18, minus 7 is 11, absolute value is 11. Check. Negative 2 times negative 2 is negative 4, minus 7 is negative 11. That checks out as well. All right, here's some functions. And remember about functions that the x or whatever is in the parentheses is your input. And so that it doesn't matter if this is a number or something else. Whatever's in here is your new x or your new input. And the function tells you what to do with it. So in words, this means 3 times the input minus 1. Take a moment and work these out. All right, so 2 slightly different problems. For one of them, we want the value of f of negative 4, so we have an x value to plug in. For the other, we're given the result. We're given, instead of the input, we're given the result. So 2 slightly different solutions. In the one where we are given the input of negative 4, we just plug in, right? 3 times the input minus 1. Watch the signs, just be real careful not to lose that, or to end up at negative 11 by going the wrong way with this minus 1. With the other one, if m is our input, go ahead and make that your new x. So f of m is 3m minus 1, and we were told that that gives a result of 17. So it's sort of like we're back solving. What would the input have to be for the output to be 17? And that checks out. If m is 6, 3 times 6 is 18, minus 1 is 17. All right, take a look at this and see if you can make these moves as the slide asks, and think about why or why not. All right, can you cancel those denominators? Can you distribute the exponent? Well, the answer is sort of yes and sort of no on some of these, or maybe more of a qualified yes. It's a straight up yes that you can cancel 9 with 3 in the example in the upper right. This clearly cancels out. This is an unqualified yes. Also an unqualified yes in the bottom right. Can you distribute this exponent? Yeah. This is nothing but multiplication inside these parentheses. And exponents are basically glorified multiplication, so no problem distributing this. This outer exponent goes on to each of the terms in there. 3 squared, x squared squared becomes x4, x to the 4th, and y squared. Everything's good there. But looking at the ones where it's not as straightforward, look at the fraction in the upper left, you can cancel. At least we have a single term in the denominator, so you can cancel the 4, but you have to do so with every term in the top. So this 4 is under each of these. It's the denominator of each part of the numerator. So this could reduce a little bit. You can cancel, but you do still have a fraction remaining. Okay, don't make the mistake of saying, oh, the 4 cancels the 4 here, and I end up with x plus 1. You'd be forgetting that it's also 1 divided by 4. In the bottom left example, you can distribute, you can square that thing, but you have to do so carefully. You can't just, pop the exponent of 2 onto the x and the y. And the reason is that this is addition. Okay, and addition is distinct from the multiplication implied by those exponents. So to actually distribute properly, you would have to write this out as x plus y parentheses times x plus y and FOIL it, first, outer, inner, last. And if you do that, you end up with this. So this brings us to the end. That was quite a lot of material, so you get a shiny star for sticking with it, and good luck on the homework.